Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations or solving systems of ordinary differential equations. Now, so far we've looked at different topics and we always solve an ODE or a system of ODEs based on the initial conditions. So it was always an initial value problem. But we can also solve some sort of boundary value problem. So we are given an ODE or a system of ODEs, and instead of having all the initial conditions for all the functions, we are given the boundary conditions for example, one of the functions or for a couple of the functions. Now you have to keep in mind that the number of conditions, whether it's an initial condition, boundary condition, should always equal the number of equations. Otherwise, we cannot uniquely solve the system of the equations, right? So sometimes there are unknowns in the initial conditions, right? So let's say we have two functions, y1, y2, and y10 is known, y20 is not known, okay? But the value of, for example, y1 at some later point is also known. So we can use that information to actually find the value of y2 at 0, the initial condition for the y2. And once we find that, we can in fact solve the differential equations and find the unique solution. So these unknowns must be solved for by knowing the solution at some other points, okay? And this translates into a boundary value problem, BVP. So it's not an initial value problem anymore because we do not know the initial condition for some of the functions. And we can use root finding methods. So basically we're going to solve the ODE anyways, okay? But we're going to define it such that the initial condition that we do not know becomes the roots of a root finding problem, all right? Which combines with our ODE solver, right? So here's an example that clarifies all these points. Let's say we have a system of two ordinary differential equations, y1 prime equals y2, y2 prime equals minus y1 plus 2. And we know that the value of y1, the first function at x equals 0, which is our initial point, is 0. But we do not know the value of y2 at 0, all right? So we do not know the initial condition of y2. But we are given that the value of y1 at some later point a is equal to 0, all right? So basically this is a boundary condition problem or a boundary value problem because from x equals 0 to x equals a, we know if these are the two boundaries of our interval that we're looking for the solution, then we know the conditions at the two boundaries for one of the functions, but not the initial condition of the other function. Well, the question is this then solvable? And the answer is yes, the system can be uniquely solved. And here's the code. So what we're going to do is we're going to define the problem such that the initial condition of y2 at 0 becomes a root finding problem, all right? Becomes the root of an equation. And what is that equation? So what we're going to do, we're going to basically solve the ODE by assuming so for different values of y2, okay? So we have y1 at 0, but we do not know y2 at 0. So we solve the ODE for different values of y2 at 0, and then we look for the specific value of y2 at 0 such that the y1 at x equals a becomes 0, and this can be easily translated into a root finding problem. So this is our deriv n function because we are solving a system of more than one ODEs, okay? And it's a real valued problem. So the functions, both of them are real. So that's deriv n function, x and z. Z is our state variable. Let me write it down here. Z is y1, y2. This is our state vector or state array. And y1 and y2, okay? So z are a state variable or a state vector. So and then this must returns the right hand side, right? The vector or the array of two equations. The first one is y1 prime, which is y2 or z1, and the second one is y2 prime, which is minus z0. So minus is here, z0 plus 2. All right, so that's the differential equations. We give a some value, let's say 5. x0 is 0, so from 0 to 5, and y1 at x equals 0, so y1 0 is 0. We already know the initial condition for the y1. And then we define an ODE system solver, because we have to pass in the deriv function to an ODE system solver, new ODE system solver. We pass in our array of functions the initial condition for x0, for the initial condition for the y0, for the y array, y1 and y2. Right now I'm passing a empty double array, so the initial conditions right now are set to 0 0. Okay, and then I define a root finding problem. So the way this works is that what I'm saying is that I look for those values of y2 at 0 such that it causes the y1 at x equals a to be 0. So I have to define a real root function, root func. The variable is y2 at 0, and I create the array of initial conditions for the ODE, because eventually I have to solve ODE, right? Each time I'm trying a different y2 0, I have to solve the ODE. So initial conditions are y1 0, which is fixed, y2 0, which is the variable of this root function, and then we set the y0, the initial conditions for the ODE system solver, to initial conditions, and then we find the solution at x equals a using, for example, runge-kutta method. So double z ODE solver dot runge-kutta at a. So it returns an array of two values. The first one is y1 at a, the second one is y2 at a, all right, which is z1. So, and we want to enforce the fact that y1 at a should be 0. And remember, real root function, when we pass it to a real root object, real root function basically a function that is solved for the variable by setting the root function to 0. So if I return the value of z0, then the root finder finds for the value of y2 0 by setting y1 at a to 0. All right. So this is our real root function. We're solving for y2 at 0, because once we have it, by enforcing this boundary condition at x equals a for y1, then we can run a final solution. We can run another solution, another round of solving ODE with these two initial conditions, and then the same old results. Okay, so the real root function y2 0 is the variable, and basically this function essentially solves the ODE with the given variable, with the given value for y2 0, and returns y1 at x equals a. And then the real root object is root finder. We pass in, and then the solution, I'm using a newton-raphson method or Newton method with an initial guess of 0 with 100 iterations. All right, and then if it finds a solution for y2 0, so if the ODE system has a unique solution, we should be able to find a unique solution for y2 0. So double y2 0 is root finder, use the Newton method with an initial guess of 0, 100 iterations, and then I'm just printing the value that it finds. And then eventually, now that I have find y2 0, I already have y1 0, so it's just doing using the ODE solver with the correct initial conditions. Set y0, now it's y1 0 and the y2 0 that we just found, all right, from the root finder. An array of x values from x0 to x0 plus 50, 1000 points, and then ODE solver dot runge-kutta for this array of x values. It returns a two-dimensional array The first row is all the values of y1, the second row is all the values of y2, and I am just plotting the results. All right, so z0 or y1 with blue color, z1 or y2 with red color. Now as you can see, we are definitely able to find a unique solution for y2 0 and then be able to solve it. And as you can see, if I look at the solution that has been found for y1, at 0 it's 0, at x equals a, and remember a was 5, it's also crossing 0. And as we expect, the solution must be oscillatory, right? So the solution is oscillatory, and we also find y2, right? y2 at 0, and as you can see, y2 at 0 is some value between 1 and 2. Okay, so this is how we can solve a boundary value problem by using our ODE solver. Now the caveat here is that, yeah, of course we need to basically when we're trying to find y2 0, we have to basically solve the ODE many times, the system of ODEs many times in this root finding process, right? And that may not be the best or most efficient way of doing it, but it's the most straightforward. And because our ODE system solver or ODE algorithm that we implemented was pretty efficient, it takes like 20 or something milliseconds to do one round of solution. So it doesn't take that much time. So let's head to Eclipse and try to actually run the code and maybe time it and see how long it takes to actually go through the whole process. So we have this ODE package, and if you recall, we have 4 driv function interfaces: driv function, driv function complex, driv end function, driv end function complex. ODE solver solves one real valued ODE. ODE solver complex solves a one complex valued ODE. ODE system solver solves a system of real valued ODEs, and ODE system solver complex solves a system of complex valued ODEs, right? And here I have this test BVP, boundary value problem. In test 1, that's the system, that's the example that I just discussed. y1 prime equals y2, and y2 prime equals minus y1 plus 2, and our state vector is y1 y2, and we're defining the root finding, we're solving. Let's look at the value of y2 0 by running, and then see what happens. So I'm going to run. As you can see, it solves using the Newton method, and with the initial guess of 0 and the maximum iterations of 100, and it's able to find y2 at 0 is equal to 1.4943627. all right, and if we look at here, the blue one is y0, and as you can see, it starts from 0, and at x equals 5 it must cross 0 again, and as you can see, at 5 it definitely crosses 0 again. And we expect to see this oscillatory behavior because y1 prime is y2, y2 prime is minus y1, so there is a change of sign. All right, so that's how we're combining our ODE solving algorithm with root finding algorithm to solve a boundary value problem instead of a initial value problem. All right, now I'm going to time this. So from here, let's create a timer, new timer, and I'm going to use the timer from my mathlib library, mathlibutil.timer, timer.start, and let's see how long it takes until we solve the timer.stop and timer.show. So we're going to see how long it takes to just run OD several times and find the y20. Takes 22 milliseconds, almost no time. All right, now let's see how long it takes to actually, after finding the and the other reason it takes very long time is very short time is because we're using Newton's method, right? If I go back to our real root object And the Newton's method, if you recall, if we don't supply the drift function, the analytic derivative of the function, it just tries to calculate the derivative using the center approximation with an order of h squared error. All right, but then it's Newton's method, or Newton-raphson method, so it's a quadratic convergence, so it's kind of like the fastest convergence that we can get. So let's put the timer here. So I'm going to time it to see. So we solved for the root, and then we solved for the ODE. It takes 48 milliseconds, almost twice as it takes for the just finding y to 0. Okay, so it's still pretty fast. It's very fast. Okay. Now in test 2, let's go back to the PowerPoint. So this is the whole idea, and we can do other things. For example, in physics, typically, especially if we look at the like waves problems or quantum mechanics problems, there is a family of problems called eigenvalue problems. Now, eigenvalue means that we apply a derivative operator or differentiation, which is linear in the function that we're looking for, and it becomes equal to some number times the function itself. And that number is called the eigenvalue of that operator. So here, for example, this is the Schrödinger's equation, time-independent Schrödinger equation. And we need to solve for the wave function psi, and also we need to find the corresponding energy values, energy states. All right, so in the Schrödinger equation, for those of you who are not familiar with it, we apply this operator, which is the kinetic energy plus this potential energy u of x as a function of space x, y, z. Here it's just one dimensional, so as a function of x. So the left hand side is the operator of the Hamiltonian, which when applies on the time independent wave function, it should return the energy state of the energy of that state, and then multiplied by the wave function itself. All right, so this is definitely an eigenvalue problem. So in quantum mechanics, we always need to solve this eigenvalue problem, and energy values or the eigenvalues typically end up being discrete values. It's not a continuous spectrum of energies. So E is an unknown, and also the psi, the function, is also unknown. But we do know the distribution of potential energy, and we also have these coefficients, mass of electron, rest mass, and the reduced Planck constant. So we're looking for E and also the wave function. All right, so E is a parameter in the differential equation that is unknown. So these unknowns must be solved for by knowing the solution at some other point. All right, and we already know that. So let's look at the example. So in a very nice abrupt quantum well, right, with a potential well, let's say from let's say the length of the well is a, and x equals 0 is right at the center, and therefore the extent of the well is from minus a over 2 all the way to plus a over 2. All right, now let's assume a simple case where the potential energy is 0 inside the well and it's infinite outside the well. All right, so that's the simplest case. And if the potential energy is infinite outside this region, then the electron can never reach enough energy to get out of the well. So the electron can never be outside this region. So we already know that this psi function, the solution of the ODE, must be 0 right at the edge and outside. If outside is 0, it should definitely be also 0 right at the edge. There's no other way, right? So no tail outside the well, and psi must, because psi is a continuous function, there is no way that psi is discontinuous. So if it's 0 outside, there is no tail outside for infinite energy outside, then right at the edge, left edge and the right edge, the psi, the wave function must also be 0. All right. So here's our example is one-dimensional Schrödinger equation in infinite potential well, and we need to find energy eigenvalues E. And because we're talking about a real electron system, the energy values should be real values and in general should be positive. There are cases where, not for electrons, for other fundamental particles, that the energy values end up being negative, but for an electron, physically what makes sense is for the energy values to be positive. So we don't know what these eigenvalue energies are, and E is an unknown, but we have a boundary condition. So this is the key. Just like the previous slide that we had a boundary condition, here we also are given a boundary condition, because physically electron can never be outside, and because of the continuity of the psi function, the electron probability must be 0 at both ends, at -a/2, at a/2, this be 0. So this is not a typical initial condition problem. We have a boundary condition problem, okay? Now furthermore, this is not a first order equation, this is a second order equation. And we already have seen how to solve this. We break it into a system of two ODEs, all right? One represents psi, the other one represents psi prime, right? The first derivative, and then we can solve that system. But again, it becomes exactly like the previous one. In this case, we also had the boundary condition on one of the functions, and we solve for the initial condition for the other one. But here, we are solving for the energy state, right? Therefore, we have to do some assumption on what the psi prime is. And if you look at the more details, if you look at actually the math of the solution, is that this psi prime eventually ends up being a normalization for the basically psi function, right? Because this is a probability, so it should have some sort of normalization property, because it's a probability at the end. So in order to find E, we need to have some assumption, or we need to assume some value for psi prime at x0, which is -a/2 at the initial point, right? So we cannot solve without knowing psi prime at x0, and also without knowing E, because we have two unknowns, but we know that this boundary condition, in order to give us a unique solution of a system of two ODEs, because this second order differential equation becomes two first order differential equations when we break it into a system of two ODEs. So here I'm just assuming that psi prime is 1. If you assume another number, the whole solution just gets multiplied by that number, because it's just a normalization, all right? So we're going to assume that psi prime is 1. So we already have established the initial conditions. We don't know what E is, so we cannot solve the ODE. So first we need to find E, this eigenvalue of the energy. And in order to do that, we solve the ODE for different values of E, and we enforce the condition that the psi at a/2 must be 0. So we again use our root finding algorithm to find the E by enforcing this equation, this boundary condition. And then when we find that, we find E, and then we can solve the ODE. Now, as you probably can guess, the energy in a the electron in a potential well can actually have multiple energy levels, right? So we expect to see an infinite number of energies. Now, the property that it should have is that these energy levels must be discrete values, and then discrete values, and for each one of them the distribution of the psi function is different. That corresponds to different probabilities of the distribution of the basically the electron. So here's the Java code, which is very simple, very similar to the previous case, but in the contrary to this slide that we solved for y20, we solved for the initial condition of the other function. Here we're solving for E. So A is 1, let's assume it's 1, and I'm going to also assume a normalization. So h bar squared over 2me, I'm going to assume it's equal to 1. It doesn't matter, we can divide everything by this and then do a change of variable for x, so it really doesn't matter. And for because we're solving for the inside of the well, the u function is 0. So our differential equation is basically y double prime is minus e times y. All right, assuming that the e is normalized to this value, which doesn't really matter. And if you do the math analytically, the solutions, the eigen energy solutions are n times pi over a squared. So in this case, it's simple enough so that we can solve for the eigenvalues, eigenenergy values analytically. So it's an integer number n squared times pi over a squared. And if a is 1, the energy levels should be n squared, an integer raised to the power of 2 times pi squared. So x0 is minus 0.5 times a, x1 is 0.5 times a, y0 is 0, y0 prime is 1, and the initial conditions are fixed, so we're not solving for initial conditions, right? We can assume anything for y prime, y0 prime, but it's just a normalization for the solution. And then we're going to construct a real root function, func e, all right? And we are looking for the e parameter by solving the ODE. So y double prime is minus ey, our state vector is y prime, because we transformed this second order differential equation into a system of two first order ODEs. Derive m function func x and z, new double, z0 is y, so z0 prime is z1, which is y prime, and z1 prime is y double prime, which is minus e times z0, minus e times y. And then ODE system solver, we pass in the function, initial condition for x and the initial conditions for y0 and y0 prime. And then we look at the solution at x equals x1, which is 0.5. So we solve from x0, which is minus 0.5, to x1, which is plus 0.5a, using runge-kutta. And then what the equation that we're trying to enforce is that the y at x1 must be 0. The solution at x1 must become 0. And this method, when we invoke it at one particular point, x1, it gives us an array of two values, y at x1 and y prime at x1, right? So z0 becomes the value of the function y, so we return z0. And then we construct a root finder, and here I'm looking for a couple of solutions. So I already know that it has to have more than one solution, or it may have more than one solution. So I'm using, for example, the trisection method for e values from 0 to 100 in this interval, and for 100 sub-intervals, all right? And then print this list of solutions. And for each value, I divide it also by pi squared. Because if this code works, the analytic solution is n squared times pi squared. So I expect to see 1 squared, 2 squared, 3 squared, and etc. All right? So let's go and have a look at the actual code. So here's the code. Test 2, initial conditions, x0 minus 0.5 times a, x1 is 0.5 times a, and we can use runge-kutta or Fehlberg or any other methods. Fehlberg was the most accurate. This was the fifth order accuracy. So Fehlberg was order h5, the one that we implemented, and runge-kutta gives us order h4. All right. And then after that, if we find multiple solutions, we can solve the system of ODE for any one of these solutions, E values, energy values, and that will give us a different wave function, right? So after, let me just comment this out first. So here I'm just solving for the E values. All right, I have to run test 2 in the main method. All right, let's see what we get. So I'm getting, after I divide the energy states, energy values by pi squared, I get 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, 4 squared, which is 16, 5 squared, which is 25, 6 squared, and 7 squared. And as you can see, the higher values, they tend to get error, right? And this error mostly comes from the error for solving the ODE, right? And it combines with the error for root finder. I mean, the error for root finder was good, so it's most likely from the ODE error. So let's increase the order of error by going to Fehlberg method, fifth order, and we expect these 16 and 25 and 36, these become closer to n squared. So we have 1, which is very close to 1, 4, 9, 16, 25. Now you see that it has the first 2 decimal places are 0. 36, the first decimal place is 0. So these become more and more accurate, all right? Okay, so now let's plot the wave function or the solution for any of these. So here I have a variable index, an integer, which picks the e value based on that, and then drift n function again is a system z1 minus e dot get index. Remember, e is a list object, so dot get at index. So I go at index 0 first. All right, so let's run an index 0. This is wave function at index 0, all right? So as you can see, at minus 0.5 it's 0, at 0.5 it's also 0, so it satisfies the boundary conditions, all right? Now if I plot z1, here z1 is basically derivative, and we already know that the initial condition was that the y1 prime or the y prime at x equals 0, at x equals x0 should be 1. So we also have that. Yes, as you can see, the y prime is 1, all right? And we needed that assumption to be able to uniquely find the energy states. So this is the index 0. So this is also called the ground state. As you can see, the electron is basically has a probability of 0 at the edges, and the maximum probability is right at the center of the potential one. Now let's look at the next index, next energy level, which is a higher energy level. So in this case, as you can see, we have to actually look at the squared of this solution. A squared of the wave function is basically the probability density, and again it's 0 at both ends as we expect. So the energy values are found such that it satisfies these two boundary conditions, and then we see that in this energy state the electron is most likely to be found at this point, and it's not to be found anywhere in the middle, all right? And so on. We can find other energy states, for example the 5th energy state or the 6th energy state is something like this. And again, as you can see, the boundary conditions are satisfied, all right? It's 0. You see we have some error, so it's not exactly 0, but at x equals 0 is definitely 0, all right? Now, as you probably can guess, this is not the best way to solve eigenvalue problems. There are better ways, using linear algebra and the matrix formulation to solve eigenvalue problems, and we will look at that in the later lectures. So in the next slide, I'm just summarizing the fact that for this one-dimensional Schrödinger equation with an infinite potential well, so potential energy is infinite outside the well, so the solution must be 0 at the edges. And as you can see, this is mode 1, mode 2, mode 3, mode 4, and we also have a mode 0 or the 0 energy, n equals 0. Basically the ground state is n equals 1, right? and that was just the ground state. So these are the analytic solutions, and again, this is the code. We construct our real root function to find the E. We need to do some assumption on the y0 prime, all right, or y and y prime at equals at the initial point, and that turns out to be just a normalization to the probability function, all right. And these are different solutions, wave function, and then once you take the square of this wave function, it gives you the probability density of the electron distribution. Okay, so I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.